Yeah, come on everyone, let's start off. Perfect. So the last thing that we did, we started solving circuits. So everyone has gone through this. We have done almost 29 problems. So we started with the dielectric stuff. Let's go ahead. We'll do a few more on this. We should be able to wrap up this in next 1 hour, and we'll start off with current, which is another quite an important topic. So this is what we did last time, series parallel stuff. So sorry. So we have two parallel plates. Let's say this lower half is made of like this. So this is made of a dielectric slab, K, and this is made of another dielectric, 2K. You're getting how it is cut? Ever seen a sandwich? So you have the wedge, that entire wedge is like a dielectric there. So that other side would be the red thing there. So the distance between the plates is D, right? It's a square plate of side A. Find C equivalent. Let's get this thing. You guys remember I gave you a tracker, the PDF and the Excel file? It is there in the dashboard now. So every time you type the questions gravitation 20, it goes to the tracker, and you can literally use the tracker for all three subjects are there. So you can check it out and see how it works. And I also minimize the number of things that you have to type now. You have to type only like 7 times you have to answer it. So do use it. It is just a tool, right? It is just to keep a track of what you're doing, and it is just to keep you motivated. Like I'm not saying, use that tool so suddenly you'll become something awesome or something. Just think of like this. Let's say Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Let's say you study 4 hours today, you study three, you don't study anything, you study 1 hour. Now, when you're typing this and you're putting it Friday, right, you will feel like, yeah, kuch nahi kar raha hu, let's do something. That's it. It will just push you that way. Maybe without the tracker, you would have studied 2 hours. With the tracker, you'll feel little guilty, and maybe you'll study 3 hours. That's it. That's it. So see, the one who wants to study, they will study with or without any system. Those who don't want to study, they'll not study with any system. Getting it? So this is for people who are really trying their best, but कुछ ना कुछ distractions आते रहते हैं. That is okay. Happens with everyone. So the inspiration is that only. When I was in 11th and 12th, right, I used to maintain a small diary. In that, I used to write every day how many hours I studied. So उसमें not big numbers like 2.5 hours, 3 hours, 1.5, 4 hours, and there will be some days like 0, 1, 1. And when I used to see this thing, right, I used to feel like, yeah, I'm not doing anything. It is showing you on your face, right? Because you're not doing anything. And then next day, because I'm feeling bad, I used to study 4 hours, whether I like it or not. So it is a way to force yourself. Like, you're just being, see, you can lie to anyone, you can bluff anyone. You can't do it to yourself, isn't it? That way. So do use it. There is a tracker now. That's a pretty useful tool. Whenever you say my rotation is bad, exactly what is bad, the tracker will tell you. Because most people come with that thing. Okay, my rotation is bad. Like, what is bad? Is your moment of inertia bad? Rotation, rolling motion bad? Angular momentum bad? In that, I even gave you an option for, what do you call? You can even change the subtopics. You can add your own subtopics, and every sheet is independent. Like, it is your own personal sheet. No one can see. So you can add your stuff. I don't have the topics for Max and Chem, but I gave it advanced portion and said, boss, make a tracker like physics. It made something. You can edit and change the way you want. So yeah, do use it. How to do this thing? Yeah, it does give you the summaries also. Every time I fire that summary, it costs me 50 rupees. Yesterday, you must have seen, you must have got 3 summaries. I was testing it. Previously, there was one more easier version. This Claude, there was a cheaper version that was costing like what, 2 rupees. But the analysis was so hopeless. It was simply telling you what it did. I said, that's not what you need. So I upgraded to a higher version. Now it is scolding you much better. But it's costing me 50 rupees every time I fire for you guys. Anyway, it'll keep firing every Sunday morning. You will get a summary at 8 o'clock. I hope it is still working. I don't know. How do we handle this? So let me give you a little idea there. See, the problem here is how will we choose your element? So there are two pieces here. So this is how we will take an element. So at a distance x, take a thin slice here. Right. So this length would be a and the thickness would be dx. So this would be the area here. So if we take this angle to be theta, which we can calculate, tan theta is nothing but the opposite side, which is the distance between them by a. So this part is covered by k, and that upper part is covered by 2k. So we can treat this thing as, and this length will be x tan theta. So we can treat this as two capacitors. Now it is so small, you can ignore that slanting thing. So we can treat this as one capacitor here with k and one green capacitor with 2k. You're getting what we did? So this vertical slab can be treated as two capacitors up and down. And these two capacitors are in what? Series, because same charge flows through them. Right? So yeah, so this distance would be d minus x tan theta. This distance would be x tan theta. So you can treat them like two capacitors. Both are in series. Let's call this thing DC1. Let's call this thing DC2. So this is filled with the red material and this is filled with the green stuff. So what is DC1 and DC2? So DC1, the formula area A epsilon by D. Area is A into dx. Epsilon, the medium is 2k, so 2k epsilon, and the distance between the plates is d minus x tan theta. Please ask me if you're confused with this. DC2 is area ADX, the same area. The dielectric constant k into epsilon. So epsilon becomes epsilon medium by distance becomes x tan theta. Please check these two terms there. So here I exaggerated the figure, but it's actually a very thin sheet. So you can assume this works. Yeah, I think Samit, that is right. And these two capacitors are in series. So what is the C equivalent? 1 by DC is 1 by DC1 plus 1 by DC2. And this would give you, when you reverse this, 1 by A epsilon K dx. This would be d minus x tan theta by 2 plus x tan theta. That would be d plus x tan theta by 2 times a epsilon k dx. This is 1 by dc. Reverse this. So this will give you dc. 2a epsilon k. This is constant. This is dx by d plus x tan theta. Integrate on both sides. This will go from 0 to a. So the C equivalent would be 2a epsilon k. This would be 1 by tan theta ln d plus x tan theta. Hope this much integration you can handle. The limits will go from 0 to. And what is tan theta? Tan theta is nothing but d by a. So if you substitute that, you get C equivalent is equal to 2a square epsilon k by d. And this thing inside will become, when you substitute a, you'll get ln 2. Check your answer. So the main idea here is how do you choose the elements there? So you take that as a vertical strip and then you finish off from there. Do have a look at the steps. Can someone tell me why can't I choose an element like this? If I choose an element like this, what is the problem? Why did I choose it only vertically? Why can't I choose horizontally? Any ideas why? Or I can do it. Yeah. Anyone else? Samyak got it. Because see, if you take like this, what is the problem? If you take like this element, do you think this potential difference and this potential difference will be same? Is the left and right side looking identical? No, right? So potential difference won't be same. If the potential difference is not same, that means these two are not in parallel. If these two are not in parallel, you can't calculate the capacitance of this junction, this horizontal piece. So you can't solve. Are you clear with this? But vertically, why it works? Because whatever charge passes through the green thing, same thing passes through the red thing. So we can be sure they're in series. So taking a horizontal element won't work here. Is that clear, everyone? So that's one more thing about C equivalent. Great. Let's see one more. Let's say we have a capacitance. This is a dielectric slab, K. This here is a conductor. This whole setup is connected to a battery. And this side is grounded, so that potential will be 0. So this point will have 0 potential, and this point will have potential V. This is x is equal to 0. This is x is equal to d. This is x is equal to 2d. This is x is equal to 3d. This is x is equal to 4d, and this is x is equal to 5d. So basically, distance between each one is d, and the thickness of each one is also d. This would be a good one. So find C equivalent. That's a pretty good mains question. Then I wanted to plot electric field versus X graph. If you're going from left to right, how will the electric field look like? Electric field versus X coordinate. Plot potential versus X coordinate. Let's get this thing. This could be because the graphs are there, it will be a good question. Like, how does the electric field and how does the potential vary? First, get the C equivalent. Let's start from there. Okay. Let's see. I don't know the answer actually. How did you get? I think maybe you're right, Ishman. We have to see. I don't know the answer. Let's see if anyone got the same thing. K epsilon. Yeah, I think you and Param got the same thing. So maybe right. Samyak also got the same thing. So yeah, looks right. Yeah, area of the plates is A. I forgot that. Okay, let's see the C equivalent. Now, the one important thing here is this. What does a conductor do? Near ho gaya. That's, I think you included the conductor. So the first thing you need to understand, what is the field inside a conductor? Zero. Remember? That means if the field inside a conductor is zero, so that space is actually useless. You cannot store any energy in that region. Getting it? So if you have a field inside a conductor is zero. So basically you can just ignore that space. You can assume there is, you can just remove that entire space and decrease the distance between them. Because if you remember the definition of a capacitor, it is the space between the plates where the energy is stored in the form of electric field. And if you don't have electric field, you don't make any sense there. You don't have anything to do there. We can ignore the space occupied by the conductor. So your picture will look like this. So remember this, huh? Quite a useful thing. So if someone puts a conductor, you can just remove that space and say it is useless. So just to give an example, I'll give an example and then we'll do this. So if someone gives you, let's say, two plates, and they say the distance is d, and they say there is a conductor here, let's say of thickness d by 3. So you know what you can do? You can actually treat this as one capacitor on the left. Now see, remember this is a conductor, isn't it? So you can treat that whole conductor like simply a wire. It doesn't matter because it's a conductor and we can just treat it to be something like this. So that will be like a wire, and let's say if this distance was d by 3 and d by 3. It doesn't even matter actually. If you take this distance to be t, so we can treat this as one capacitor T. We can treat this one capacitor as D by 3 is ignored. So 2D by 3 minus T. So this is as good as considering the whole thing as one capacitor with the new distance 2D by 3. Is this making sense? That is what I mean by ignore that space. Matlab, you can literally remove this D by 3 distance from here and bring the plates closer. So this guy is as good as keeping 2D by 3. And this is independent of where you keep the conductor slab. You can put the conductor in the middle, to the side, to the corner. It's not going to affect your answer. Is this clear, everyone? So you can remove this entire conductor and replace that with a conducting wire. It's not going to affect your problem because what is the field here? Field here is zero. What is the field here? Field is equal to zero. It is useless. Are you clear what we did? Any doubts on this? Please ask me if you're confused about this part. Right? So then, yeah, going back to our question. So in our question, now we have a dielectric and a conductor. Now dielectric you can't remove. So let me take it step by step for you. So first let's remove the conductor. When I say remove conductor, I'm literally removing that space also. Remove the space where conductor is present. The new picture will look like this. So you have your dielectric here. Okay. This distance was D. This distance was D, and this distance was 2D. So the distance became 4D. Now here, one more thing. It, like I said, it really doesn't matter where you keep the dielectric slab. You can keep it anywhere. Answer will be same. But let's prove it. Like, yeah, it doesn't depend. So this can be treated as three capacitors. We can treat this as one capacitor, the green capacitor, and this capacitor. So I can treat this as three capacitors. This is the capacitor K with a distance D. This is a vacuum capacitor with distance D and a vacuum capacitor with distance 2D. All these three are in series. So 1 by C equivalent will be D by A epsilon plus D by Ka epsilon plus 2D by A epsilon. So did you notice? These two will always add up. So it doesn't matter where you keep the dielectric. So when you do this, this would come out to be how much? 3D by A epsilon by D by Ka epsilon. Yeah, you can simplify this and you end up with A epsilon by D. Take out that common and you end up with 1 by K plus 3. Yeah, you can simplify that further. Got this? Maybe I should get it reverse, I guess. 3 plus 1 by K, so it will be 3 plus K by K. Yeah, I will get reverse. K by 3K plus 1. Got this? Any doubts on this part? All clear with this. Like before going ahead, let's see just one more example. Tell me the answer for this because this is a very important mains and bits model. So let's say we got a capacitor here. Let's say we kept a conductor here, dielectric here, K. It was not mentioned where it is. So let this distance was X and let the distance was D. Right? So can you find the just capacitance of this? Get it fast. Simple question. Find the capacitance of this system. Thickness also I need to give, sorry. Let the thickness be T. So a dielectric of thickness T, distance between the plates is D. It is at a distance X from the left-hand side. Find the capacitance of this system. And if you do that, you will get an answer independent of X. And that's what I want to tell you. It doesn't matter where you keep the dielectric. So you'll get the same thing. So whenever you give a question like this, you can push the dielectric to one corner and treat it as two capacitors. Normally, this would be like three capacitors, this one, and this one. So we can treat this as three capacitors. This guy has a distance X. This guy has a thickness T, and this guy has a distance of D minus T minus X. This was filled with K. All the three capacitors are in series. So 1 by C equivalent will be X by A epsilon. This is T by Ka epsilon. This will be D minus T minus X by A epsilon. When you add them, you can clearly see that X cancels off. So it doesn't matter where you keep the slab. So T by Ka epsilon. Take out 1 by A epsilon common. You end up with D plus D minus T into 1 minus 1 by K. Reverse this. So we get C equivalent is equal to A epsilon by D minus T, 1 minus 1 by K. That's your result there. Standard Means and bits level equation. Now here, if you say this is a conductor, then K will be infinity for a conductor, then you can clearly see this term becomes 0, isn't it? Then you get the distance is D minus T. So that's what I was saying. If it was a conductor, you can just ignore that space and treat the distance as D minus T and you're done. You get an answer. All clear with this? So pretty standard model. You should definitely remember this. I'm sure this will pop up in some question, some exam. See, you guys will be writing a lot of exams. 2 mains, 2 bits, 2 CETs, right? So Manipal, Vellore, all, there are a hell lot of exams, UGE exam. So you'll be writing almost like 9 to 10 exams. So standard questions do pop up. Question still not over. We have to find the electric field and potential. How do we go about that? If you remember the discussion we had about electric field inside a dielectric. So let me show the picture how it looks. Here, let the field be E. Can someone tell me what will be that field ka value E? It's a good one. If they ask you what is the actual value of the field in that space, what is the value there? So that conductor is useless, isn't it? So if you remove that conductor, the field here will be simply the potential difference by 4D. That formula is always valid. Potential difference by distance is the field. Clear with that? Yeah, it will be V by 4D. It doesn't depend on the dielectric. The potential difference between these two plates is V. You can ignore the conductor, so the distance becomes 4D. Now, if this is field E, inside a dielectric, what is the field? E by K. What is the field outside? Again E. What is the field inside the conductor? 0. Once you come out, field is E. So the field will always keep going. And do you remember, right, why the field becomes E by K? This we did in the last class story, if you remember. The reason was the induced charges. The induced charges will create a counter field which will try to oppose this, and that's the reason the field inside becomes E by K. Great. So that's it. Once you know this, now let's plot this graph. So let's plot the E versus X graph. So from 0 to T, the field is E. Then the value suddenly drops to E by K. Then again it increases. It's like a step function. Then it drops to 0 inside the conductor. Then again it increases. So this is how the graph will look for E versus X graph. Is the graph clear, everyone? So maybe I'll just remove the dotted lines though. Yeah. How will the potential graph look like? If you remember, field is nothing but minus dV by dx. That means this is the negative of slope in Vx graph. So the electric field is nothing but the negative slope in a Vx graph. So when you're plotting a Vx graph, the slope of this must be the electric field. So initially you're starting from 0. Initially field was E, so you will be decreasing. And then suddenly your field is there, but the field decreased, matlab slope decreased. So your graph will become little more flat. Then again, it is E. Inside the conductor, potential becomes constant. So it'll become a constant line and then you'll decrease again. So this is how the graph looks. So this would be theta. This angle would be some alpha. This angle would be theta. This angle would be theta. D, 2D, 3D, 4D, and 5D. So it's like E is equal to minus tan theta. E by K is minus tan alpha. So the slope will vary. Are you getting how the graph looks? Drawing the graph is difficult, but if they give you four options, it is easy to eliminate them. Any doubts on the graphs? So the slope in a Vx graph will be the field. So if the field is constant, the slope is constant. If the field is zero, then the line should be horizontal, a flat line. Others, do keep your cams on. Do keep your cams on during the session. Any doubts on this? It's a good problem. Definitely check it out. We did a lot of things in this. Let's see the next one. We have a capacitor with a battery. We did something like this before, something like this. So case one, the battery is removed. Case two, battery is present. So you removed the battery, you kept the battery. And now what you did, you introduced a dielectric between them. You took a dielectric slab K and you introduced between the space. If you remember, the previous question was the distance between the plates was doubled. Yaad hai wo question? So here a dielectric slab is introduced between them. Then what I want you to find, I want you to find the new charge. So options will be, it became K times, it became 1 by K times, it will remain same, yeah, something of that sort. The new capacitance, the new voltage, the new field, new force between the plates, energy stored, energy density, seven quantities. Exact same question, we did it before, but there I said the distance between the plates is increased. This is case one and case two. Seven questions, two cases, 14 things total. Let's get them. If this was a question, I will ask you force between the plates. And you can ask anything, but yeah, that's one thing you have to be little careful. Let's get that. Let's see. Let's see case by case. Let's see case one first. So case one is when you remove the battery. And you know what happens when you remove the battery? The charge will remain constant. So initially, if you had charge Q, where Q was CV, if you remove the battery, charge cannot change. So Q remains same. So that is the first thing. So what is the new capacitance? Remember the capacitance ka formula is A epsilon medium by D. You introduced a slab K, so capacitance becomes Kc. Charge remains same, Q. What is the potential difference? Q by C. Q remained the same, but capacitance became Kc. So potential becomes V by K. What is the field between the plates? Field between the plates is potential difference by distance. The potential difference became V by K. Distance remained same. So field also becomes 1 by K times. Now, the force between the plates. This is the interesting thing. You have to be careful. When you say force between the plates, right? The formula here is Q square by 2A epsilon. This is not epsilon M. This is vacuum only. This is not epsilon medium. The reason, when you keep the dielectric slab, what are the charges on the plates? The charges on the plate is plus Q and minus Q. What was the question? Force between the plates, isn't it? The force between the plates is independent of any other charges. Even if you take the net force, think about this. This will be minus Q induced and this is plus Q induced. The dielectric slab will not exert any force on the plates because minus Q and plus Q will cancel. So that is the main key point there. Force between the plates is independent of the slab. It depends only on the charge on the capacitor. Because plus Q minus Q, they will exert equal amount of force. Matlab, it is like this. If you're still confused, if this is plus Q, listen to this. This should make things clear if you're confused. This is minus Qi. So basically, this will be an infinite sheet, isn't it? Minus sigma I. This also will be an infinite sheet plus sigma I. Okay. Now, what is the field of minus sigma I? It will be towards the sheet, which is sigma I by 2 epsilon. What is sigma I ka field? That will be away from the sheet, sigma I by 2 epsilon to the right side. This and this will always cancel, isn't it? So the charges on the dielectric slab will not exert any force on the guys outside. So they will always cancel out because an infinite sheet will always create an equal and constant field. So is this clear? So that is one mistake what people do because unka, you know what people remember? They remember force is q square by 2a epsilon. And they will think, अरे यहाँ पे medium है ना, तो epsilon medium. So they will think force became 1 by k times. Are you clear with that? I hope you didn't fell into that trap. So that could be a mistake. So you have to be careful there. So yeah, so this is the force between the plates is independent of dielectric. So did the charge change? No. So the force will remain same. What is the energy? Q square by 2c. Q remains same. Capacitance became 1 by k times. So energy becomes k times. What is energy density? Field became 1 by k times. यहाँ पे what is the formula again for energy density? Energy density ka formula is half epsilon medium E square. So epsilon m became 1 by k, k times. E square became 1 by k square. So the overall thing becomes 1 by k times. Are you clear with this? So in the energy density formula, half epsilon E square, that E is the epsilon medium. So that becomes k times and epsilon E square becomes 1 by k square times. So energy becomes k times, energy density becomes 1 by k times, force remains same. I scribbled it a bit. Any doubts on this part? Quite an important question. It's a pretty good one. Not difficult, but you have to be careful with things. Clear. Now, can you do the case two? I'll give you a minute. Same story, but this time there's a battery present. So if we keep the battery, voltage remains same. So let's see how to handle that. Okay, let's see. The voltage will remain same. So this is V. Capacitance becomes a epsilon medium by K. Did I do a mistake here? No, I did it wrong. This is Kc. So the charge will change. So charge becomes K times. So it will be Kq. Field ka formula is V by D. Potential didn't change. Distance didn't change. So the field will remain same. So that is a thing. That formula is always valid. So what actually happens, right? Because you put the dielectric, charge becomes Kq times, right? Because of that, the field becomes K times, but that epsilon m becomes K times. So Kk will cancel, field will remain same. So force between the plates, yeah, now this will change because Q square by A epsilon, the Q became K times. So the force becomes K square. Energy is half CV square. So this becomes K times. This guy is again half epsilon m E square. So field remains same. So this becomes K times. All clear with this? Clear with this? That's the question on that. So we have done something similar previously. There we said the distance between the plates was doubled. Here we are saying we're putting a dielectric slab. And these are very, meaning if you see, right, we are doing like literally what, 14 questions there. Anything could be a variation there. All clear. Any doubts? Anyone not convinced with anything? Not sure? Please ask. You can always unmute and ask. If you're feeling shy, you can always type in the chat box to the co-host here. Great. Let's go ahead then. The last part that we have is the force on a dielectric slab. So let me show you how this works and then we'll go ahead. Force on a dielectric slab. So what exactly happens? So let's say if you take a dielectric slab and if you just introduce it near the plates. So let's say we got our dielectric slab here. And let's say you introduce this between the plates. So what happens? So this will have a plus charge. This will have a minus charge. This is your dielectric K. And now you will have an induced charges here. Now remember, these charges will be non-uniform distribution because there is no symmetry there. This will be some induced charges on the dielectric slab. Now, if you remember, in the beginning, we said something. When we started this whole thing about capacitors, there was one big thing we did. The distance between the plates must be very small. Page 94, Gauss law. If you actually take the plates, the fields on the edges, right, will actually be at an angles and all. This is the fringe field. We ignored this because the distances were, very close and all. But when this thing is coming from the, the edge, what actually happens, there is a fringe field here. So there are field lines which are going like this. So there are some fringe field lines. Now, because of this field line, see what happens. So on this lab, these are all negative charges. These are all positive charges. the field lines are going, this way. So the force will be this way, opposite to the negative charge. And this is the positive thing here. So the force will be this way. Can you see how the force is acting on that field? So this F is the force due to the fringe field. And if you see here, this is kind of symmetrical, meaning we are assuming the slab exactly fits in the gap. So because of this fringe forces, so the net force will be on the left-hand side. This will be F net. So that means whenever you take this dielectric slab and if you keep it near the mouth of the capacitor, the fringe field will pull the slab inside. The net force due to this fringe field is towards the slab, towards the, the capacitor. Field pulls the slab inside. The more the slab inside goes, the more, the force will be there and it'll just keep going inside. Once it goes completely inside, then the force will cancel out and you'll get a zero force there. Pulls the slab inside. This story is clear. Why there will be a force in the first place? So that means you have a capacitor, you take a dielectric, you just bring it little close to the corner. Matlab, this is the plate. You bring the dielectric and just put it here and leave it. It will start going inside automatically. Without doing anything, it will get pulled inside. Now we want to find this force. Now, normally you cannot find this force directly because the fields are non-uniform, charges are non-uniform, it is a mess. So, but there is a way to handle this. So let's first get some variables. So let's say we have a capacitor plate. We have a battery, voltage V. Let's say these are square plates of side L or side A. And you introduced a slab between the plates, and let's say it is already gone inside by X. So it is something like this. Are you guys able to visualize the 3D structure there? If I just have to show you the side view, it looks like this. The slab is gone like this. So this part of the slab is already gone inside. The 3D looks a little bad, I guess, but I hope you understood. You're getting how the slab is being pushed inside? So this part is X inside. So now the slab is X inside. So let the dielectric slab be X inside. Just fit inside. So we are assuming there is not much space. And be X inside. Great. So that means we can treat this thing as it just looks big and all, but it's a good derivation. You need to know the derivation, though. It is also there for your HSC. You can also get good advanced questions on this. So I'll show you how they can ask you this. So this is how it would look. So the X part is inside. So this part is covered with a dielectric. And the other part is not covered with dielectric. So this is distance X. And this area would be A into X. This distance will be D minus X. And this area will be A into D minus X. Length into breadth, basically. So this can be treated as two capacitors. Both are in parallel because they have the same potential difference. The right side is filled with a dielectric K. So what is this capacitance? This capacitance is area, which is A into D minus X, epsilon by distance between them. Wait, I'm mixing up D and L, I guess. Sorry, this is A minus X. This was D. This was A into A minus X. Yeah, that was the thing. So what is the area there? A into A minus X epsilon by D. What is this capacitance? K times area AX epsilon by distance is D. Are the capacitances clear, everyone? So you can divide the capacitor into two parts. The part where it's a dielectric, part where it is no dielectric. And both of them are in parallel. So we get C equivalent is equal to C1 plus C2. Add them up. You get A epsilon by D into A minus X plus KX. So this will give you A epsilon by T into X into K minus 1 plus A. This is important. Remember this question. This will again come in current electricity, which you're going to do later. And then, now how do we get force from here? We got C equivalent. So then the energy stored is half C equivalent to V square. This is connected to a battery. Anyone remembers how to get a force from energy? F is equal to minus du by dx. That is how you get the force. We don't get it from Coulomb's law or something. We get it from energy. So differentiate this function. So when you differentiate this, you end up with minus A epsilon V square by 2D. If you differentiate this function with X, that A is a constant, you end up with K minus 1. You get a pretty interesting answer. You get a constant force. Observe this. It does not depend on X. Whether the slab just entered or the slab is like 1/4 inside, or it doesn't matter. The force is always constant. The negative sign indicates attraction. So the slab is always pulled inside with a constant force, which the result you should definitely remember. You won't have time to derive in the exam. And it's a standard result. Definitely should remember. There were exam questions where this formula itself was a question. You know the result, you put it there and you're done. Please have a look at the derivation. The derivation is important. In case you forgot, you should know how to derive this in less than a minute. So you treat it as two, let it be X inside, treat this as two capacitors. They both are in parallel, get C equivalent, half C equivalent V square and differentiate. Is the process clear, everyone? Now, if I want to make this into a little decent equation, like in advanced easy equation, they'll ask you, what type of motion is this and find the time period. What kind of motion is this? What do you guys think? Most common mistake, sabko lagta every time it will be an SHM. For SHM, what is the condition? F should be proportional to X power 1. Isn't it? It should depend on the displacement. Here the answer is independent of X. This is a periodic motion. It's not oscillatory also. Even in oscillatory motion, the force should depend on X. Yeah, right, Srihari. This is a periodic motion. The motion repeats itself. That's it. There is no, the restoring force does not depend on X. If you go back to the definition of, oscillations, look at the definition there. Oscillatory motion, the restoring force is towards the mean position, right? It should depend on the X part there. Here, there is no mean position there. There is never a point where the force be 0. So the equation should depend on X. SHM, it is proportional to X power 1. So they can ask you how to find the time period. So that will be also a pretty good question. If you know the result, you can handle most of the questions here. So let me show you how it would look. So if you take the slab and leave it from here, let the mass of the slab be M. So just now we got the force F, where F is equal to A epsilon V square is the voltage by D. Remember, there is a battery, I'm not drawing it, into K minus 1. So from here, we get the acceleration is F by M. Let this length be A. So what is the time taken? T is equal to, we use the formula, A is equal to half into acceleration T square, S is equal to half AT square. So we get T is equal to root over 2 times A by acceleration, which is F by M. So how will the motion look like? Look at this picture. This is how it looks. So this was the slab. T0, you're here. And then let's call this thing as capital T. When T is equal to capital T, you will completely go inside the capacitor. You will be here. At this point, you have maximum speed. T is equal to 2T. You will come out from the other side. Because of velocity, you'll go this side. Now the force will be backward. So here the force will be this way. Slab will completely come outside this way. The force will be inward. Then at T is equal to 3T, again you will enter the capacitor. You will be exactly in the middle. This time again you will have a maximum speed, but this time towards the right. Then again you'll come back to the initial position. You'll come back to T. So from here you will come back again here, right? Maybe I'll draw one more picture there. So you will again come back to the initial position here. The force will be inside and the time is 4T. So this motion repeats after itself every time after 4 times time period. So the time period of this motion is 4 times T, which is 4 into root over 2a mass by F. F ka value, you can substitute there. Is this clear, everyone? This is a periodic motion. So if I keep the slab on the edge, it'll get pulled inside and it doesn't stop. It'll keep going left, front, back, front, back. It'll just keep oscillating. I'll show you how to make this an advanced question next, but let's finish off with this. All clear with this? Now in this, let me show you one more question, how they can ask you these things. That's it. It's not a big concept. If you know the formula, you can handle most of them. So just let's do one more thing. Let's say we have a dielectric liquid. Rho is the density and K is the dielectric constant. Then what you did, you brought two capacitor plates with a battery V, area A, and D is the distance between the plates. These are square plates of side A. And D is the distance between the plates. Now what happens? The capacitor plates will think the liquid is the dielectric slab. So you will get some force on the dielectric slab and the liquid will actually start rising. The liquid starts rising between the plates. Height h. Find h. Gravity is present. Find h in steady state. So this system, right? Normally what would happen? The liquid would actually go up and down. We're ignoring that. Ignore surface tension and everything. You can bring all that, but let's not do that. If you add surface tension, याद है हमने ऐसा क्वेश्चन surface tension में भी किया था. Two plates are placed on a liquid and the liquid rises up. Then the net height will be due to surface tension plus capacitor ka force. So yeah, let's get this. Yeah, the question is big, but if you actually see, you'll get this in 2 steps. Yeah, that looks right, Arya. Let's say try others. I'll give you a minute though. So how do we do this? It's a pretty straightforward thing if you know your result. So when the liquid rises here, what are the forces acting on the liquid? You have the attraction force F and you have your mg. Bus. So these two must be equal. And this height is h. So force is equal to mg. What is the force? A epsilon v square by 2d into k minus 1. What is mg? Density into volume. What is the volume? So the volume would be this entire slab kind of thing. This was distance d. This was the side of the plate, and this was height h. So A d h into g. So again, you'll get h from here. A will cancel. Uh, so yeah, you're left with epsilon v square k minus 1 by 2d square rho g. Yeah, I think that's your answer. Is that clear, everyone? That's it. So if you know the force on a dielectric slab, question is straightforward. And then from there, you'll get it. Most people don't remember the result, so do make sure to remember that. Any doubts on this? All clear with this? Take a break. Come back by 9:45. We'll continue from here. We're done with the chapter capacitors. We'll start off with a new chapter, current electricity. So we have done almost 33 questions, 150-page notes. So it's a big one. So make sure to revise this. Should definitely start solving and finish off capacitors by next Tuesday. Take a break. Come back by 9:45. We'll start a new one. Any doubts so far in capacitors, you can ask me. Okay, come back by 9:45. Yeah, let's go ahead. Next thing is current electricity. Quite an important chapter, has a pretty high weightage because the way JE people have classified this chapter, right? One is current, and second thing they call it as electrical instruments. Now both belong to current, but yeah. So that way it is pretty good. So if I have to compare this with mechanics, think of like this. Current electricity is like work power energy in mechanics, something of that way. So again, so let's go ahead with this. So what is current? We'll start off with that, and I think maybe we'll just play with the current part today, the definition. Current, the symbol we use small I. Pretty straightforward definition. It is the rate of flow of charge. Others do keep your cams on. Again, don't worry about writing the notes. You'll get the PDF. So focus, listen, understand. Not sure with something, please ask, get your doubts cleared, and do the questions. When I'm giving you time for the questions, make sure to spend time and try them. And the direction of the flow, the direction is the flow of positive charge. Flow of positive charge is taken as the direction of current. So if the positive charge goes forward, we think that is the current direction. So initially people defined current like this, and then they realized, boss, actually electrons are the ones which move. So they should have actually named the electron as a positive charge, but already done, so can't do anything. So if a positive charge goes this way, then we say current I is flowing this way. If a negative charge goes this way, then we say current is flowing opposite to the negative charge. So be careful with that convention. So the thing is, the flow of positive charge is taken as current. So straight definition, I is equal to dq by dt. That means if you integrate this, we get delta q is equal to integral I dt. You can also write I average, that is nothing but delta q by time. The net charge by net time will give you the average current. They're pretty straightforward definition. I is dq by dt. Means if you take a graph between charge and time, so in a qt graph, the slope will give you current. In a current versus time graph, the area under the curve, so area above is positive, area below is negative. So integral I dt, the area under the graph gives you the charge flow. Gives you delta q. So they can ask like this, they can give you a graph and they can ask you to do this stuff. And just a point there, current has direction, but it is not a vector quantity. It doesn't obey vector laws of addition. It's actually a tensor. We'll not get into that. If you remember the definition of a vector, the quantities which have magnitude, direction, and obey vector laws. So current is not a vector. It doesn't obey vector laws. Clear with this? There, straightforward definition, I is dq by dt. That's it. So that's the only thing. So let's do a question on this. We have a particle of charge q going in a circle with speed u in a radius r. Find the average current. The charge q goes in a circle. of radius r with speed u. Find average current. Second thing, we got a charged ring which is rotating with omega. Lambda, r, and omega. Lambda is your linear density. This is a rotating charged ring. Find current. Let's get them. Let's look at the first one. Straightforward definition. What is the current? Charge by time. What is the charge? Q. What is the time? It takes 2 pi r, the circumference, by speed u to complete one revolution. So average current is Q by 2 pi r. Easy. So if you're looking at one point, it completes the circle after every one revolution. So charge by time. What about this thing? This you can do in two different ways. You can take the total charge by time, or you can take a small piece, d theta. So we get dq is equal to lambda into rd theta. Lambda is the linear density and rd theta is this. So current I is nothing but dq by dt. This would be lambda r d theta by dt, which is omega. This is actually instantaneous current because every instant the charge is flowing. Here, this is average. Is this clear, everyone? Lambda or omega? Remember that first question, huh? We will do that again in modern physics, it will come. You know how they'll ask the question in the exam? I'll give you an example. Say, an electron in the hydrogen atom is going in the nth orbit. Then the current I is proportional to n power x, find x, where n is the principal quantum number. That is the actual question they would ask you. You guys want to try? Try. An electron in a hydrogen-like atom is going in the nth orbit. The current I of that electron is proportional to n power x, where x is the principal quantum number. Find x. I hope you guys have done chemistry and atomic structure, so you should know those results. But that would be the actual question. Zero nahi hoga second mein. Basically, see, if you just look at this cross section, charge is continuously crossing that area, right? So current ka definition is charge, crossing through an area every second. Is that right हो गया? Clear ना? इसका क्या करना था? Look at the formula here. So I is proportional to U by R. You guys remember in atomic structure, what is U? U is proportional to Z by N. R is proportional to N square by Z. Remember this? So that means this is proportional to 1 by N cube, isn't it? So current is proportional to N power minus 3. You guys remember that? Velocity of a nth orbit is V naught by N. Radius of an nth orbit is proportional to N square. So you should know those formulas of atomic structure. So that would be minus 3. So, but anyway, don't worry, we'll do that again in atomic structure. The same thing, we have one more variation of this. This is an important one. You should definitely remember this result. We have a proton beam. So you're sending a proton beam with speed v. area A, n is the number of protons per unit volume. Charge of a proton is E. So find the current. So if you send a proton beam, it's like a current only. This is the area of cross section. This gives you feeling of water jet ka question. Okay, let's see. Hmm. Consider a small cross section. Consider a thin section here, dx. So in this section dx, how many protons are there? Number of protons will be n, number of protons per unit volume into A into dx. So what is the total charge in this thing? So charge in dx will be n into A dx. That is the number of protons into E. E is the charge of a proton. So we got dq is equal to NEA dx. That is the charge in that. So what is current? Dq by dt. Dx by dt is velocity. I is equal to NEAV. Remember this, huh? Pretty good result. You should definitely remember this result. Standard result. So if a beam or something is going with speed v and n is the number of protons or particles per unit volume and E is the charge of that particle, the current is NEAV. Okay with this? Easy stuff, good ones. So let's see something better now. Any doubts on this? Next one. Let's say we have a conducting shell. We have an ammeter and this is grounded. What is an ammeter? It measures current. This is a conducting shell. Radius r. At a distance r, we have a charge q going with speed u towards the center. When the distance is d between the center and the charge, we observe there is some current in the ammeter. Find current when plus q charge. Is that distance d from center and moving towards it with speed u. Now, let me explain you the story again. So there is a conducting shell which is grounded. Grounded means potential zero. There is a charge here which is coming from some distance and it is getting closer and closer and closer. When this charge is getting closer and closer to the shell, something happens and you get a current in the ammeter. Now, for a minute, think and figure out why the hell there is a current. Then I'll tell you why there is a current, and then I'll give you 1 more minute to solve. So first think what is happening and why there is a current. First figure out that. Take a minute. If you can figure it out, then go ahead with the question. Because if you don't figure out why there's a current, the whole thing will look like, what the hell is this? This is Gauss law and current electricity. And remember, I taught you only one concept till now, I is equal to dq by dt. That's it. I didn't teach you anything else in current. This is a question from Gauss law. So as the charge gets closer and closer to the conducting shell, something happens and you get a current. So you need to figure out why there is a current and how much is that. Okay, let's see why there is a current. First of all, ask yourself, if there is a charge Q here, right, this will have some potential here. But because you're grounding it, so what will happen is this plus Q will create some induced charges here. Do you guys agree? As this plus Q is coming, it will induce some charge on the conducting shell. Now, because of this induced charges and because of this charge, remember, both of them together, the potential must be 0. Do you guys agree? Whenever you ground a conductor, charge can flow from the earth to the conductor. So as you get closer and closer, as this plus Q gets closer and closer, you'll get more and more negative charge. If you're getting more and more negative charge, means more and more charge is flowing into the earth from the conductor. The flow of charge is called current, isn't it? So as you get closer and closer, charge keeps on flowing. If the charge is flowing, means it's called current. So that is the reason why you're getting a current. Is that reason clear? So how do we start? So start like this. Since it is a variable, don't take distance d, take it as distance x. Let the charge be at a distance x. Let the conductor ka charge be small q. This is the induced charge, or this is the charge from the thing. So find small q in terms of x and differentiate, you'll get the current. Let's see. So when the charge is at a distance x, let the induced charge be small q. So potential of the shell will be 0 since grounded. So as you get closer, the plus q, you should get more small q in order to compensate for it. Sorry, V is 0 and E is also 0. So K, Q, R, D plus R near area. D is the distance between the center and the charge directly, right? So D is the distance till here. It's not till the surface. Okay, let's see. What is the potential of the shell? Potential of the shell is due to two guys, K, Q by X. Everyone agrees why K, Q by X is the potential of the shell? Because the field inside the potential is 0, shielding effect, it is grounded. There is no field inside. So the whole region is 0, equipotential. So this is equipotential. So if you can find the potential at the center, that will be the potential on the surface also. plus K small q by R. The Q is the, this is the charge from the earth. And since this is grounded, this should be zero. The question looks a little dangerous, but it is actually easy to solve. So small q will be minus q r by x. So there, see, as you get closer and closer, you get more and more charge. I is equal to dq by dt. This would be qr by x square dx by dt. But be careful here, dx by dt is minus u since x is decreasing. So we get the current is minus q r u by x square. The minus sign indicates, I thought current is coming here. Actually, current is going into the earth. The minus sign indicates the direction is reverse. Q is not positive. So negative indicates current is going into earth. It's a good question. You should definitely check it out again. So as the charge gets closer and closer, you can clearly see the charge from the earth is increasing more and more. And if a charge is flowing through a wire, that's what we call as current. Any doubts on this? Grounding, Gauss law, current electricity. You can put x is equal to d, that will give you the answer. U is missing now, yeah, dx by dt. बाकी सब right था. All got this? Let's see one more like this. We have three parallel plates. This distance is d. This distance is d. These two are connected by a wire, and we have an ammeter here, and these two are connected with a wire. This guy has a charge plus q. This guy has a charge minus 2q, and this thing has a charge plus 3q. And now what happened? The middle plate started oscillating in SHM. X is equal to a sine omega t. So the middle plate, right, is oscillating left and right. If you oscillate left and right, what will happen? The distances will change, isn't it? If the distances change, then the charge will keep flowing left and right in the ammeter. If the charge is flowing, it's called current. There. SHM Gauss law current. Again, SHM is not really a big deal that I gave you the equation. Actual question that I'll give you two springs here and I'll ask you find the time period also. But we'll do that later on. X is equal to a sine omega t, and you can be a is less than d. We don't want to go and touch the other plate. So find the current in the ammeter. I can make the distance 2D, 3D. Yeah, it is the same thing. So let's see how will you handle this. You guys remember that relation between the two plates? Q1, D1 is Q2, D2. Forgot. ये formula याद है? Whenever you have two plates with the distance D1 and D2, this is the formula. This charge into this distance must be equal to this charge into this distance. If you forgot this, you can't do this question. It's page 103, Gauss law. So यहाँ पे whatever charge is there, this charge into this distance is equal to this charge on the right side into this distance. That ratio is always same. That product. Now try. Okay, let's see. So see, when you do this kind of questions, right, always assume it has moved by a distance x. So the picture will look like this. Let this thing go by distance x. So this thing has moved by distance x. Then what will happen to this distance? This distance will become d plus x. What will happen to this distance? This will become d minus x. Right? So, and what is the charge distribution? Hope you remember. So the charge distribution here will be total charge by 2. So that would be q, 3q plus q. So the charges on the outermost plates is q total by 2, which is q. This is q. Let this be q1 and let this be q2. Now q1 into this distance, q2 into this distance must be always equal. This we proved in Gauss law. So q1 into d plus x must be equal to q2 into d minus x. But we also know q1 plus q2 is 2 minus q, because the total charge on the middle plate is conserved. Solve this. So what is q1? Minus 2q minus q2 into d plus x is q2 into d minus x. So bring all this to one side. This would be q2 minus 2q. This will be minus 2q into d plus x, and it goes that side, and q2 into 2d. So we get q2 is equal to 2 will cancel minus q by d into d plus x. It's not really that bad. That's your minus q2. So you will induce here minus q2, and here you'll induce minus q1 here. Any doubts on the chart distribution? Now, once you got this, let's draw the picture again. What are the charges? So outside the charge is q. This was minus q2. Now, can I say like this? Whenever this current I is flowing into this plate, it is changing the total charge on the right plate, isn't it? The rate of change of this charge is the current in the plate. So current I can be defined as d by dt into q minus q2. So basically current here is the rate of change of charge on the right plate. You can do this also. If you say, no, I want to take the left plate, then this is q and minus q1. Current I is going here. You can say current I is minus, because the current is leaving there, dq, q minus q1. This also works. Both are right. You can either say this plate is losing charge. You can say this plate is gaining charge. Either way it works. Uh, capital Q is constant. So current I is simply minus dq2 by dt. We know what is q2. Take it and dump it here. How much is this? Q by d differential d by dt of x plus t. D is a constant that goes off. So you'll get q by d dx by dt. Dx by dt is a omega cos omega t. Yeah, it looks deadly, but it is not. So q a omega by d cos omega t. This is the current. See what we did. We generated AC current using a movement of a plate. By moving the plate in the middle, we can create an alternating current. Other steps clear, everyone. So the main thing was getting the charge on the right plate. And this formula we know from Gauss law. So the biggest headache was getting the charge only. The current part was actually easy. You have to just differentiate. Any doubts on this? This is how they can frame a question. This is how the questions will be in advance. And this will be an advanced or moderate level question. I mean, it could be a good single choice question or an integer, integer or more than one choice. If they really decide to harass you guys, then that's a different story, though. They'll put three things like this. They'll put springs in the middle, and then they will say it is disturbed by small x. You have to find that time period also, and then we have to do the whole thing. But anyways, clear with this. All clear with this? You can see what is happening, right? We are going back to all the old questions. Let's see one more. We have a capacitor here, square plate side A. D is the distance between plates. This is connected to a battery with an ammeter. And now what happened? We have a dielectric slab. So initially it is just outside. This side is A. This is going inside with a U with a constant speed. The dielectric slab enters this thing. This is the time t is equal to 0. I can actually say I left it. It will oscillate. You can find the current, but you can do that also. But let's keep it simple for now. A dielectric slab of length A, which is exactly the side of the plate, right, enters a capacitor with constant speed U. It exactly fits the capacitor. No space between them. Enters a capacitor with speed U. Plot current versus time graph. So current in the ammeter versus time. Meaning, just to give an idea, after some time the slab will go like this. After some time the slab will completely enter, and then the slab will start coming out, and the slab will completely leave. So the slab doesn't care. Slab is just going straight inside the constant speed U. Plot current versus time graph. Capacitors and current. And Sol Nashi here. It's not. That is wrong answer. Okay, but how will the graph look like somewhere? There is a trap there. Yeah, right. That was a trap. See. So let's say this thing is already gone X inside. And this guy will look like just now what we did, the force on a dielectric slab. So some part of the dielectric is occupied, capacitor is occupied by dielectric. Let this be X. And the remaining space will be A minus X. The distance is D between them. We can treat this as two capacitors. Remember, it is like left and right. So this is like one capacitor and this is like one capacitor. The terminals are left and right. So this upper part is filled with K. So both are in parallel. So C equivalent will be the area. How much is that? So if you see, this is the area there. This is X. D minus X, and this is A. So the area would be A X K epsilon by D. The second one will be area A into, this is A minus X. K minus X into epsilon by T. It is exactly the same thing, everyone. See, exactly same stuff. Instead of up and down, it is left and right. We get C equivalent will be A epsilon by D into A minus X plus Kx. What is the charge on the capacitor? Q is equal to C equivalent into V. A epsilon V by D into A plus X into K minus 1. What is the current? I is equal to dq by dt. When I differentiate this, we get A epsilon voltage V by D into K minus 1 dx by dt. Be careful, dx by dt is PDU. So this is A epsilon V K minus 1 PDU by D. That's your current, and this is constant. It's constant magnitude. Check, this should be the value of the current. So as the dielectric enters inside, you get a constant current in the battery. Yeah, there's a small trap there. Question is still not over. Right, Utsa. So if you just look at the picture, what is happening, right? The current actually changes direction. Look at this. So T0, you are just outside. Okay. Now, as you're entering inside, the charge is increasing. So as you're entering inside, C equivalent increases. Because the C equivalent increases, Q increases. Because Q is increasing, the current is flowing into the battery. Current is going into the capacitor. So the battery is giving you the current. The current comes out of the battery. So battery is discharging. And then when you are completely inside, you have reached a maximum value. So this will happen when time is equal to A by U. After this point, the capacitor starts coming out. If the capacitor is coming out, the C equivalent is decreasing. Agreed, current is still same, but Q is decreasing. So the charge is going back into the battery. So current is going into the battery. The current reverses direction. And finally, when it comes out, you're gone. C remains constant and current becomes zero. So if you try to plot the graph, current versus time graph, this is what you will notice. Again, we are assuming coming out of the battery is positive, they'll give you. So they have a constant current. Then the current is constant, but magnitude will change. And then you'll become zero. Most people mess up this part. They realize it is constant and they will just draw like this answer. So this time would be A by U and this time would be 2A by U. The current reverses direction. So this is I and this is minus I. Are you clear with that difference? Okay. Yeah, then it is fine. Is this clear, everyone? The next thing, we'll define a small thing called current density. So even though current is not a vector quantity, we have a quantity called current density. This is a vector quantity. Current density, the symbol is J bar. J is simply defined as current per unit perpendicular area. So if you have a wire like this with the slanting cross section, this is current I, this is J. So the J ka direction will be the direction of the current. This is the cross section. Let's say this is the area vector A bar. This angle is theta. This is how current is defined. So current I is given by J bar dot A bar, which is JA cos theta. So current is not a vector quantity, but current density is a vector quantity. The direction of J bar is along the current. So later on we will see. You must have studied in school, right? V is equal to IR. There is even a more powerful version of Ohm's law, which comes in terms of J. So J is quite useful when you're dealing with things, where the current is flowing in different directions or something like that. So this is current density. So it is simply current per unit area. Clear with this? Let's do one simple question on this and then we'll wrap up for the day. Let's say we have a cylinder where the current density J is J naught into 1 minus small r by capital R, where R lies between R to 0. R is distance from the axis. So this is a solid cylinder. So in this solid cylinder, there is a current flowing, which is this is the current density is changing like this. Look at this. When R is 0, current is maximum. So maximum current is flowing in the center. As you go outside, the current decreases and becomes 0 here. So find the current in the cylinder. There, simple integration. There's nothing there. So J is current per unit area. But here, your current density is changing with R. At the center, more current is flowing. As you go outside, current decreases. So how much current is flowing through the cylinder? This J is your current density. J naught is a constant. How do we do this? Yeah, right, Samyak. Param, nere param. Limits, you have the limits, right? Why can't you just substitute 0 to R? So see how we do this thing. So how we do? At a distance x, take a thin cross section. So take a thin cross section x at a thickness dx. So the current in this small thickness di will be current into area, which is 2 pi x into dx. So this dx is so small, you can assume j is almost constant and multiply with this area. So the current I will be integral, j will be j naught 1 minus x by r, or you can take 2 pi r dr, whichever you like. 2 pi x dx, the limits will go from 0 to r. बस इतना ही करना था. This will be j naught 2 pi. When you integrate this, this will be x square by 2 minus x cube by 3r. Limits 0 to r. j naught pi r square by 6. 6 or 3. Wait, I messed up something. Yeah, 3. The 2 is there in the numerator. Clear with this? Bus, there's nothing much. Itna hi karna. But more about this J, right? We'll use this a lot in magnetism later on. It has more uses there than here. But anyway, so that's a bit about current. So there, all we did today was simply what is current, dq by dt, and what is current density. So next class when we catch up, we will continue more from here. We are going to see the series circuits, parallel, all the things that we learned, but in a little different way. One of the most neglected parts that we will see. We have some really, really good questions there. So next class will be quite an important one. Okay, so with that, we'll wrap up for the day, right? So start doing capacitors. Again, I keep telling you, don't keep any backlog from now, right? Take a week ka time, finish off capacitors or your class ka material, jo bhi hai, HCV, DCP, your class ka material, jo bhi hai, complete one material thoroughly, right? And do remember, Saturday there is a test, so make sure to give it. So we'll catch up again on Thursday, same time. So any doubts, anything else, please stay back and ask, or else you're free to leave. So take care, stay safe.